first of all, hello everyone, and welcome to our 5th Continuum Wind Energy Software Town Hall. As always, it is really great to see lots of familiar names and faces, and also a warm welcome to all the newcomers attending today's session. For those of you I haven't had the chance to meet yet, my name is Liz Walls, and I am the lead developer of the Continuum software. And I'm also the Director of Renewable Energy Services at One Power Company, or OPC for short. And it is through OPC that we have been able, Aaron and I, over the years, to build out the various wind resource assessment modules in Continuum and to provide the software as a free and open source tool for the industry. And joining me is my colleague, Erin Reckley. She is the product manager of Continuum, and she has the title of Principal Energy Advisor at OPC. And we have some really good material to get into today. So let's jump in and take a look at today's agenda. Okay, so first thing on the list for today is we are continuing our wind flow model lecture series that we're calling the Continuum Wind Flow Model Explained. So today we'll be covering part 3 of a 6-part series. And in today's session, we'll be exploring the surface roughness and displacement height components of the model. So we'll be looking at land cover types and how those are converted to surface roughness and displacement height, and how we have incorporated or used the log law profile to take into account changes in roughness and how that impacts wind flow. Following this, the lectures portion of the presentation, we'll open it up right away to any questions that you might have, maybe about the material that we covered today or a question in the software. Anything at all is allowed, so we'll have that part open for any questions you may have. And then at the last part of the town hall, we'll be going over some development highlights in the software. So Erin and I have been talking about a few new features that we're considering to add to the software. And we've also been talking about the future of the software in terms of the framework that we use. So we're excited for this part of the town hall because we're looking for input from all of you. So we'll have you basically vote for the different features that you think would be most useful or that you're most interested in. So make sure to stick around for that. We're really anxious to get your input. Okay, so let's just jump right in to the wind flow model series. Before we do get into the surface roughness portion of the model, we wanted just to give a quick recap of what we've covered so far. Again, today is part 3 of a 6-part session. If you missed the previous town hall or missed previous sessions explaining or the first 2 sessions on the wind flow model, those videos are all available on YouTube as well as on our website. So you can feel free to go and review those if you missed them. Anyway, so what I'm showing here is the full model equation for the Continuum wind flow model. And what we did in session 1 and 2 is we focused on the first 2 terms of the model. And that is related to the upwind and downwind, so that's UW and DW, the upwind and downwind terrain exposure components, as well as the different flow types. So we looked at uphill flow, downhill flow, as well as induced speed up over a hill. So that was the first 2 sessions, and that is some of the main building blocks of the Continuum model. In today's session, we'll be shifting gears a little bit, and we'll be focused on surface roughness and displacement height and how changes in those values impact wind flow and how we estimate in Continuum changes in the wind speed due to these variations in roughness and displacement height. In the following session, we will cover the last 2 terms of this model, and those are the elevation component as well as the valley component. So that will be session 4, which we'll do in a couple of months or so. Session 5, we'll start getting into terrain complexity and how that relates to model coefficients and how we're able to have model coefficients that vary depending on terrain complexity and how that further enhances the model. And then finally, session 6 ties it all together where we explore or explain the machine learning algorithm that we use in Continuum, which finds the model coefficients for a given site based on cross prediction and minimizing the error between met sites. So that will tie it all together, and that will complete our 6-part series. So with that, I'll turn it over to Erin.
Yeah, so thanks, Liz. Kind of giving a big recap of the entire model equation and the little bite-sized pieces that we're taking as we go through this seminar series. So Liz was saying for this session, we're talking about surface roughness and displacement height. And these are probably some words you may not have heard of before. So what is surface roughness? I wanted to go. So surface roughness is just kind of the idea that it quantifies the texture of the Earth's surface that affects how the wind is going to either slow down, well, it's going to slow down due to friction right near the surface. And it's described by this parameter called the roughness length. So the roughness length, usually denoted by Z naught, that roughness length, it's a length scale. So it's an actual kind of measure of length that it represents the height at which the mean wind speed theoretically goes down to zero if you're extrapolating using the wind profile down to the surface. And we're assuming the log wind profile and there's no obstacles. I said a whole lot of words. We'll get to all of them though, I promise. So this roughness length, you just kind of need to think about it as it's seeing, okay, how is the surface texture really affecting what the wind is doing right above the surface? So this roughness length, it's accounting for the surface drag. So the friction, the drag that the surface is having on the wind right at that surface level. So there are a bunch of different tables out there through various agencies. Mostly they're similar numbers, but what it does is it takes different types of terrain, so land cover and terrain, and it says, all right, if I am a specific type of terrain, this is my on average roughness length. So this is how much yeah, I guess let me rephrase that a little bit. So if I have a really small surface length or a roughness length number, means that the surface isn't going to be as grabby onto my wind. Whereas if I have a large roughness length number, the surface is very rough, there's a lot going on, and it's really going to be impacting the flow right at the surface. So the World Meteorological Organization, that's a pretty common table to kind of have that correlation between what terrain type you have and what that surface or that roughness length is going to end up being. So the larger the roughness length, the rougher the surface. Kind of how I was saying, the bigger the number, the more grabby the surface is to the wind itself. So we're talking about that log wind profile. So let's kind of look at that equation. What does that all have to do with it? So there's a simplified log law wind profile that is basically, it's just an empirical formula, and it's used to calculate the wind speed with changes with respect to height. So how is the wind changing as you go up in the vertical away from the surface? And we're going to be assuming neutral stability so that nothing is really adding or taking away from the winds or your air's ability to go up or down. So with this log law wind profile equation, it does take into effect the surface, or it takes the effect of the surface into the calculation using the roughness length, as well as a thing called friction velocity. So here's our kind of simplified log law equation. We have our wind speed at a specific height z. So we're trying to see what is our wind speed at height z is going to be equal to this u star, which is our friction velocity. So friction velocity, it's just the measure of shear stress that's exerted on the wind on a surface. So how much the surface is pulling on the wind. So you can kind of, yeah, how much shear stress is having on the surface. And then we've got that, so that friction velocity divided by a constant, this von Karman constant, it's 0.4. And then those two variables at the end, we have our height, so what the height that we're looking at, that we want to see what the wind speed is, divided by our roughness length. So that's where this roughness length starts to come into play, how the surface is impacting what the wind is doing in the vertical. Why is this not wanting to go? Okay, so this is kind of a pretty simple graphic to explain what this wind profile looks like as you go up in height. So the y-axis is our height in meters above the ground, and you can kind of think of the x-axis as wind speed. So as you're going up in height, you start increasing your wind speed And all the decrease of the wind speed right near the surface is due to that surface. So that red line, that's what our wind speed is doing. And you can kind of see we've got different levels, we've got different wind speeds that we're hitting. So in a really urban area, we've got lots of high rises, a lot of pavement and just a lot of obstacles in our way. We're going to have a higher roughness length where the wind speed isn't going to, or it's going to slow down a little bit faster. Whereas if we kind of move out from our urban area into not quite rural, not quite suburban, but in that middle area, we can kind of see how that wind speed profile shifts a little bit just by changing what that roughness length is. So our Z naught goes down substantially because we don't have those big sky rises. We don't have a lot of things kind of impacting the wind in the way. And if we look just at these two different profiles and the heights where those 30 meter per second wind speeds are happening, 30 meter per second wind speed is happening probably around 170, 180 meters in the city center, whereas when we're in the outskirts, it's lower. So the surface isn't impacting that wind speed in the vertical as much as it is in the city center. Take it one step further, let's look at an area, open land or open sea that doesn't really have much of anything. It's got a very, very smooth surface. So we have a very small roughness length. And we can see here, the shape of our wind profile, so the shape of the wind speed with relation to height is fairly different. And again, the only thing we're changing is that roughness length. And so we get to 30 meters per second, much lower in the atmosphere, kind of above ground level than we do in the city center and everything. So that is roughness length. It kind of adjusts that's how fast and how gravity right at the surface the wind is. But we also need to consider this thing called displacement height. So displacement height, it's the height above the ground where the mean wind starts to feel the effect of the surface. So this is accounting for the vertical shift in our wind profile. So instead of kind of that red line that we're seeing starting at 0, it's just going to bump it up and it's going to start a little bit higher up based on whatever your displacement height is. So you're basically changing what the effective ground level is with this displacement height. So we can see, bringing in some more of these figures, if we have a 0 displacement height, our profile starts right at the ground, right at 0. But if we start to add in a lot of obstacles and things around it, we're basically bumping up that surface that the wind is starting to feel the effects a little bit higher. So we have to account for all of these obstacles that are on the surface that are going to be impacting the wind speed, as we go in height. And so so this displacement height, you could kind of think like as a rule of thumb, back of the envelope type determination, it's around 2/3 to 3/4 of the height of whatever obstacles are in your way. So if you've got a 20-meter building, you can kind of think it's going to be around 12 to maybe 15 meters displacement height. You're just bumping up that kind of effective ground level based on all of those obstacles that are in your way. So similar to kind of having a surface type related to roughness length, we can add a column to that table and add what that displacement height is, kind of an on average, what you would typically expect to see based on whatever your land cover is. So these are some generic numbers that you'll start to see with your roughness lengths and displacement heights based on the different type of land cover or terrain type you have. So again, you're going to have a lot lower of a roughness length and a lot lower of a displacement height, the smoother the surface, because again, the surface isn't impacting the wind flow much at all right at that surface level. But if you do have a lot of terrain changes not terrain changes, but variation of the surface, texture on the surface, as well as a lot of obstacles on top of that, you're going to have a very large number of your roughness length and a large number of your displacement height. So the roughness length and the displacement height, they are very much related to each other. So if you increase one, you're most likely going to be increasing another. So we're going to kind of circle back to that simple log law profile equation, and we're going to look at it a little bit more in depth now, kind of knowing this concept of displacement height. So we're going to take that, that simplified law wind profile and just make it a little bit more complex. So this, the full log law wind profile, we're going to start taking in that displacement height into consideration. We're also going to start taking stability into consideration. So stability, atmospheric stability, has to do with how likely is your little blob of air wanting to go up or wanting to go down. So if you have very unstable, it means your blob of air wants to move in the vertical. Whereas if you have very stable air, it's just going to kind of sit where it is. It doesn't really have a desire to move up or down in the vertical. It just wants to stay where it is. So this, the full log law wind profile law, it takes that stability into consideration as well as the concept of displacement height. So this is what the equation is, kind of fully brought out, and it looks very similar to what it was before. The only thing that we've really added is in that top portion of the natural log, we just subtracted out our displacement height to kind of bump up where that starting ground level is. And then we added in this psi. Well, so we got our displacement height, and then we added in psi, which is our stability correction function. And so but like I was saying, this accounts for the effects of stability within, you know, our profile law. Like if it's a very unstable vicinity, then you're most likely going to have your parcel of air, you know, rising up a lot faster. So that's going to affect how your wind profile is going to look. And so this is just kind of a graphic that shows putting everything together. So we have the height of our buildings. Remember, height of the buildings is related to our displacement height. So that displacement height, it's our about 2/3 to 3/4 of the height of our buildings. And then we bump it up just a little bit more for our roughness length. So the roughness length is kind of where our wind speed is going to be hitting 0, whereas the displacement height, that's our and one more quick note, just kind of to keep in the back of your head as we're moving through and especially going through a lot of these parameters. So in Continuum, the stability correction function, that is a coefficient, and it is it gets learned, you know, we'll talk about that later on, you know, and later it gets figured out what those are. But it's not just one number for all of the model. We do have multiple coefficients that are generated for different flow types. So we've got for the downhill, for the uphill, as well as the induced speed up ones.
All right. Thanks, Erin, for that, for going over the log law profile. Really good background to have as we get to how we use the log law profile in the Continuum model. So if you attended the last couple of sessions, you might recall from the derivation from the exposure part of the model is that the key in Continuum is that we're looking at the wind speed difference between two sites. So in this model, we always assume that we know the wind speed at site 1, and we're trying to estimate the wind speed at site 2. And so in this part of the model, we're looking at how do the roughness and displacement height differences between the two sites, how do those translate to change in wind speed? So we use the log law profile, and we're going to go over the derivation of how this part of the model was derived from the log law and how it's incorporated into the Continuum model. So as I mentioned, the key is really wind speed difference, right? We know the wind speed at site 1, trying to estimate the wind speed at site 2. So here we have delta wind speed, simply the difference between the two. Now we're going to bring in the log law profile, which Aaron just explained. So this is no different from what we looked at in the previous slide, right? Now we're just looking at the wind speed profile at site 1. Can you see my mouse, by the way, as I'm moving around? Excellent. Okay. So this is the log law profile at site 1, the log law profile at site 2. You'll notice we have Z02 and D2 and stability 2. So we have the surface roughness, displacement height, and stability correction at site 1 and site 2. So no big deal, pretty similar to what we looked at so far. But Aaron did mention that we have this term, the friction velocity. Well, what can we do about that? Well, we know this wind speed at site 1. So with that in mind, we can rearrange this first equation and express the friction velocity in terms of the wind speed at site 1, as well as the displacement height and roughness at that site. Next, for some simplifying assumptions. So in this model, in Continuum, we are assuming that the friction velocity is approximately the same at the two sites. So it's in the same general area, the same project area. The stress on the surface is going to be about the same at the two sites. So that's one of the simplifying assumptions in this model, is that the friction velocity is the same. So if we make that assumption, then we can plug in the definition of the friction velocity that we have expressed in terms of the wind speed 1 into the equation for the log law at site 2. So when we do that, this shear profile at site 2 looks like this equation here. So all we've done, again, is just substituted in the definition of friction velocity, where we have it in terms of the wind speed at site 1 and the log law profile at site 1. Okay, great. So now we can express site 2 in terms of site 1 parameters, as well as the difference between the roughness and displacement height at the two sites. Taking it a step further, because again, we're interested in the delta wind speed. It's all about the change in the wind speed between site 1 and site 2. So what we're doing here is we are taking the equation for the wind speed at site 2, substituting in the equation for the friction velocity, minus the shear profile at site 1, again, substituting in the definition of friction velocity to have all the terms in this equation, things that we know, things that we can estimate and solve for. So a little bit of rearranging, some canceling of terms and combining some terms, the overall equation for the change in wind speed between two sites due to the difference in the roughness and displacement height, as well as the stability correction, turns out to be this equation here. So this is all derived from the log law, and one simplifying assumption, again, is that the friction velocity is approximately the same. Okay, now that is the basic equation, but we want to remember how we look at things in Continuum. So what we do with the terrain exposure portion of the model is we look in the upwind direction for each direction sector. And in the upwind direction, we look at, what are the changes in the upwind direction between the two sites and how will that impact the wind speed? And then we do the same thing in the downwind direction, and we look at the differences in the terrain and how that can impact the wind speed due to changes in the downwind. Well, we apply the same logic, the same concept when dealing with roughness and displacement height. So for each direction sector, we use the same inverse distance weighting to come up with the overall average roughness and displacement height, again, within each direction sector in both the upwind and downwind directions. And then we're able to estimate how much the wind speed is likely to change, again, due to the changes in the roughness and displacement height in both the upwind and downwind direction. And this is done in every direction sector, and then it is overall, and then it will be combined in the end. So we're interested in how the wind speed changes due to changes in the upwind and downwind direction. We've derived this equation shown here based on the log law profile. So we are going to substitute that in. And so you'll notice the green subscripts as well as the blue, just denoting that we're looking at the effect of the wind speed due to changes in both the upwind and downwind direction. So we separate them out and examine how those changes are likely to affect the wind flow. Okay, so now, since again, part of the model, one of the first things that we covered in this lecture series is the changes in wind speed due to the upwind and downwind terrain exposure. So these this set of this part of the model we covered in session 1, session 2. We have the model coefficients for the upwind exposure, looking at the difference in the upwind exposure, as well as the coefficient for the downwind exposure and how the changes in the downwind exposure affect the wind speed. So that's the first part of the model. And now we are adding in the change in roughness and displacement height and how that affects the wind speed. So when we were developing this model back in the day, we started off just with the exposure part of the model, just focusing on that, because actually at a lot of sites, the roughness doesn't change a whole lot. So you can make the assumption in certain situations that the roughness doesn't change very much. But in other situations, there is variability in the roughness, and you need to estimate how the wind flow is going to change due to those. So the original model just focused on exposure, and then we expanded it out to also include roughness and displacement height using the equations that we just shared in the last slide. So expanding it all out, here we are now, almost to the full wind flow model, almost the full equation that I showed on one of the first slides. So we're getting there. We still have 2 more terms to get to in next session. But up till now, we have now defined how the wind speed is likely to change between 2 sites, first on the upwind and downwind terrain exposure. So the terrain exposure is how much does the terrain vary between the 2 sites. And now we've also added in these terms to account for changes in the roughness, displacement height in both the upwind and downwind direction. So that is the continuum model up to this point. A couple more terms to go, as I said, but we're getting there. We almost have the whole model defined. Okay, so now shifting gears a little bit, talking more about the software specifically. You might be wondering, okay, so how do you define roughness and displacement height? You know, Aaron just explained that we can have varying roughness and displacement heights for different types of land cover. How is that defined in the software? Well, what we do is we use a land cover key in Continuum, and that converts land cover codes to equivalent roughness and displacement height on a gridded basis. So in the software, on the input tab, you can click the button, select view, modify land cover key, and it will open up this, this form, which shows a number of the built-in land cover keys. So the one we're showing here is for the US's National Land Cover Database, but we also have a European land cover database, North American data set, as well as a South African land cover key that we've added just in the last 6 months or so. If you don't see the land cover key that you need in this dropdown in one of the built-in land cover keys, you can always import your own. It's just a simple CSV file with the land cover code, the description, and the associated roughness and displacement height. If you want to do some research, and we'll go over some sensitivities in a few slides here, but if you want to understand how does changing these values impact my wind flow model, it's very easy to do. You just select any of these land cover keys and click modify, and then you can change the roughness and displacement height and rerun the numbers, you know, and do some research and try to understand how sensitive your site is or how sensitive your wind speed estimates are to differences or different assumptions of the roughness and displacement height. So that's a little bit on the software and how you do those modifications. And now let's move on to, oh, I missed those parts. That's okay. On to you, Aaron.
So this is just kind of, again, explaining those codes. That's the actual data that you're importing into the Continuum software. And then it's just correlating to those different roughness lengths and displacement heights. So like Liz was saying, we've got a couple sensitivities to show you, okay, if you change things around, how is that going to affect your change of wind speed between 2 sites? So if you remember, we had a couple wind farms that we've kind of been using over and over again as examples. So we're just going to be looking at Kingfisher winds today and looking at some sensitivities in the surface roughness and displacement height. We picked Kingfisher wind. It's in Oklahoma. It's a very flat site. So we're not adding a lot into the terrain exposure, kind of the wind speed changes that are going to be due to the exposure. So we can really see what the surface roughness and displacement height, or the changes in wind speed due to surface roughness and displacement height a little bit easier. So we've got a handful of kind of sensitivities to look at for that. But before we looked at any sensitivities, we're like, okay, we need to see what are we actually seeing with the real data without doing any adjustments first. So using the actual data, this is the 2 turbines that we're looking at, T24 and T28. We're looking in the upwind sector of 330. So that means the downwind sector is going to be 150. So on the left-hand side, that's our elevation data. So again, you can see it's pretty flat. There's not a whole lot of variation going on in this project area. And on the right-hand side, that's our land cover data. So those are different land cover types that are imported directly into Continuum. And it's showing the land cover type as opposed to the parameters that are associated with it. So all of that kind of like rust brown color, those are the land cover types of row crops. So you can think like wheat or corn or something like that, that these crops grow fairly, not fairly tall, but taller than me most likely. So we're having a surface roughness of 0.25 meters and a displacement height of 1.3 meters. So it's kind of raising that effective ground level pretty a good amount. Whereas kind of that beige color, that's going to be grassland, so way smoother, not as much kind of impacting what the wind is doing in the vertical. The surface isn't making as much of an impact. So we got a smaller surface roughness as well as a smaller displacement height. And then just for kind of reference for all of these sensitivities, we're going to be looking at 80 meters up. So our Z for all of our examples, we're going to say Z is going to be 80 meters. So doing all that inverse distance weighting, like Liz was talking about, in those specific sectors, for each of those two turbines, we can kind of start building out a table of what values we're going to start using within our equations. So the exposure, that's all going to stay the same. We're not changing the elevation, but our roughness lengths and our displacement heights, kind of, if you look kind of in a column, those numbers are pretty similar. So the upwind for both T24 and T28 for the roughness length, they're similar-esque, especially in the downwind. They're very close in number. So we're not going to start expecting to see very big changes when it comes to wind speed changes between the two, because they are very similar sites. So we're going to assume, all right, so we had a Met Tower, let's say, right at T24, and we measured a wind speed at 8 meters per second. And then kind of on the table to the right, those are all of our coefficients that we determined beforehand. So we bring back that big equation, not as scary as it looks, but there's just a lot going on in it. And we start plugging in all those numbers that we have in the top two tables into our equation. And you can kind of see we've got 4 different terms. So we've got the upwind and downwind exposure, and then the last 2 terms, those are our upwind and downwind surface roughness, displacement height to terms. So the total change of wind speed at this specific site is going to be just under 1/10 of a meter per second. So T28, so that site or the turbine that was a little bit to the southwest of T24, it's just going to be a little bit higher than T24 in this sector. But where we want to look specifically at what are the surface roughness, what is the change of wind speed just due to that surface roughness, and it's even smaller. So it's maybe like 1/3 to a quarter, or yeah, about 1/3 of our total wind speed change is just due to the surface roughness changes between the two sites. Keep that in mind as we are going through these next couple of sensitivities of what that value is. It's a pretty small number for our change of wind speed.
Great, thanks, Erin. So that was sort of our base case sensitivity. So after we did that, Erin and I said to ourselves, well, what would happen if we modified some of those roughness and displacement height values of those land cover keys? So the first sensitivity that we're going to show is we wanted to see what would happen if we made the row crops taller and rougher and made the grass lower and smoother. We want to see, out of curiosity, how would that change the model, or change the estimated wind speeds, I should say. So what we're showing here are the actual surface roughness values. Not showing displacement height, they're related, but for visual purposes, we're just showing roughness here, so we can keep track of how they're changing for the sensitivities. So there's the actual roughness values for the row crops that the roughness is 0.25 meters and for the grasslands is 0.03. So these are the default values that are in Continuum. For our sensitivity, we doubled the roughness and displacement height in the row crop. So now it's 0.5 meter in roughness, 2.6 meters in displacement height, and again, made the grassland smoother and with this lower displacement height. So divided everything by 2. We wanted to see how will that impact things. So here we have a similar table to what Aaron presented with the average upwind and downwind roughness and the average upwind and downwind displacement height. And again, remember, we just doubled the row crops and we halved the grasslands. And as you can see, the roughness and displacement height at both sites have gone up. And the reason for that is because there are row crops surrounding both sites as well as grasslands. So it impacted the overall roughness and displacement height at both T24 and T28. But let's plug the numbers in and see how that changes things. So here's our equation looking at the changes due to exposure as well as the wind speed changes due to the upwind and downwind roughness. Plugging in our numbers now with the higher roughness and the higher displacement height due to those row crops. And what we see is that the change in wind speed is actually reduced, which I thought was pretty interesting, but it makes sense when you think about it because again, both of the turbine sites, T24, T28, have row crops both upwind and downwind. So by raising that value, it affected the average roughness at both sites and actually reduced the expected difference in wind speed between the two sites. So we thought that was pretty interesting. So with that increased roughness in the row crops and smoother grasslands, it actually estimated a more common wind speed between the two sites, less of a difference due to the changes in roughness and displacement. Oh, you're muted, Aaron.
Oh, man. So we saw, all right, so just changing those numbers, but you have the similar characteristics and an amount of those different land types with each site, it's not making that big of a difference. But what if we put big lakes, both upwind and downwind of, one of the turbines, just one of them. So we're saying, okay, one turbine has big lakes, both upwind and downwind, and the other is going to stay how it was. So again, we've on the left-hand side, just again as a reference, that's what we currently have. Sorry, it keeps muting. Whenever I hit spacebar, it wants to mute. And so we're like, all right, let's throw these big lakes in, upwind, downwind of T24 and see how that's going to affect the wind speed. So this is the land cover, kind of in that upper right-hand corner. So everything that's blue, we have surface roughness of very, very tiny and no displacement height. So there's going to make a pretty big impact. Well, you would think that there's going to be a pretty big impact because most of the land cover within those sectors are going to be now water. So that's the land cover in those two different turbines, T24 and T28. And here are the surface roughness values. So just for a comparison. So the two dark blues are kind of hard to distinguish, but kind of in the sectors for T24, you can see the really dark blue within those sectors. It's a bit darker than kind of the other darkish blue. I would say there's like a navy blue and then like a dark blue. So there's a slight difference. So it does have a much lower surface roughness value than those other areas. So looking at these kind of now average Z knots and Ds for T24, they have gone way, way down from what we had seen before. So our T28, that's stayed the same from our base case, but now our roughness lengths and our displacement heights are much, much lower. So let's plug those in and see how is that going to affect what the change of wind speed is between the two. Plugging everything in, we've got our 4 terms, and we start seeing, oh, okay, there's some negatives in here. That's interesting. And the overall change of wind speed is going to be a negative value. So the the wind speed at T28 is actually going to be lower than what we were seeing at T24, which again starts, if you start thinking about it, it makes sense. At T24, we have those lakes, so there's not as much surface texture to grip onto that wind speed. So we're going to have a higher wind speed at T24 relative to T28, where we have a lot of kind of surface going on and it's grabbing onto that wind speed and slowing it down. So if we added that water, both upwind and downwind of T24, we actually saw that T24 was going to be higher than over at T28.
Then we decided, let's do one more sensitivity, but in the other direction. So very similar sensitivity to what Aaron just presented, but now we're going to say, what if we had an urban development city on both the upwind and downwind side of T24, right? Yeah, T24 is up there. So that's where it's shown in red. So the average roughness for urban, highly populated area in Continuum is a surface roughness of 1.6 and a high displacement height, 13.3 meters. So this is considered, imagine there's a city on both sides, upwind and downwind of T24. We want to see how that's going to impact the wind flow model. This plot is showing the actual roughness values, and the red is corresponding to that higher roughness due to those urban development land cover codes that we imposed on this map. Going back to that table with all the different values, now we can see in this situation with that urban development area upwind and downwind of T24, really high surface roughness in both the upwind and down direction and really large displacement heights in both the upwind and down direction. We're going to plug those numbers in, see what happens, and not too surprisingly, it estimates a significant increase in wind speed between site T24 and T28, because at T28 you just have row crops and grasslands. You don't have these big buildings to contest with that are slowing down your wind speed. And so in this model, it is estimating a change in wind speed of 0.38, with 0.33 of it due to the changes in the roughness and displacement height, specifically that urban development upwind and downwind of T24. So that should give you an idea of the variability and the sensitivity of the model to changes in the roughness. So again, feel free to do some research on your own to play around with these parameters and see how they impact the resulting wind speed estimates.
And so just to kind of put everything onto one slide so you can see it all right next to each other, what the change of wind speed is just due to those surface roughness, both upwind and downwind components. Again, between our actual, our baseline, or the baseline, and then when we changed the row crops and made smoother grasslands, when we added in the lake at T24, how that affected the wind speeds, as well as the urban development, those big cities, both upwind and downwind of the city or of T24. So it does make a difference. The surface roughness type and the land cover, the roughness lengths and the displacement heights that are chosen, they do make a difference. And so using kind of the built-in ones, those are pretty standard and accepted throughout the community to be using. But definitely play around and see if I change something, what happens. Absolutely.
Okay, well, there's one more thing to get to. Can't forget about the stability parameters. So we've been talking about, or maybe you've noticed that the stability coefficient we've assumed was 100. But you might be wondering, well, what is that? Can it change? And yes, it absolutely does. And so by modifying that value psi, it impacts how sensitive the wind speed changes are to changes in roughness. So let's do an example, look at an example of how this coefficient impacts the estimated change in wind speed. So first of all, I just wanted to mention that in Continuum, the stability coefficient is defined using an exponent alpha. And so on this plot here on the x-axis, we're looking at the exponent. So it goes from 0 to 3. If it was on a log scale, it'd be going from 1 to 1,000. But it's just easier to show the changes in this format, looking at the exponent on the x-axis. So we were looking at our baseline example with the baseline roughness and displacement height, and we're modifying the stability coefficient to see how that changes the estimated change in wind speed. And so as you can see, as the stability coefficient reduces, as it goes to the left, the change in wind speed increases. And just know that a lower stability coefficient is represents a more stable atmospheric condition. Another way to think about this, so Aaron talked about the blob of air wanting to move upward. You know, there's a lot of vertical mixing in unstable air versus stable conditions. There is less vertical movement, there's less mixing. Another way to think about it is during stable flow, the flow is almost laminar, not quite, but it's approaching laminar flow. And in situations like that, the wind is more coupled to changes in the surface. So if there is a change in roughness, the wind responds more to it in stable atmospheric conditions versus unstable, where there's a lot of vertical mixing, a lot of chaotic activity. The wind is less coupled. It doesn't feel the changes in the roughness as much. So with a higher stability coefficient, that represents unstable conditions where the change in wind speed is, again, less sensitive to changes in the roughness. So that's how we're able to tie in atmospheric stability, which, as we'll talk about in future sessions, is really quite important for wind flow modeling. The next example looks at, what if we were to double the roughness? Well, in this situation, we see with a higher difference in the roughness and displacement height between the two sites, in stable conditions, there is even more of a change in the estimated wind speed. So the stability coefficient not only impacts how sensitive the wind speed changes are, it also is related to how rough the surface is. That also is another parameter that takes that has an impact. So that concludes, I think, yes, that concludes the lecture portion of today's town hall. Again, that was part 3 of a 6-part session. So that means we're halfway through, which is very exciting. So we're excited to get to the next 3 sessions. And we do have some continuum development highlights to get to. But before we do, just wanted to open the floor if there are any immediate questions, concerns, comments that we can get to. If not, maybe you need to think about it a little bit. Maybe we'll just jump into the continuum development highlights. But I'll just pause for a second, see if there are any comments or questions. Okay. Well, we only have about 11 minutes left in today's hour, and we're excited to get all of your feedback on what development highlight or what future features and future of our framework of the software, what you want to see. So I'm going to go over, I think, 5 or 6 proposed new features that Aaron and I have talked about. And as I'm doing this, if you could open up your the chat, Aaron will be typing in the okay, thanks, Bauer. Yeah, appreciate you attending. Aaron is going to type out these proposed new features. And I want you to listen to them all, and then I want you to vote for the top 2 that you think would be the most beneficial to you as a user. So the first one, power curve density correction. This has come up with a few users. You may have noticed in Continuum, you can specify the air density, but it has no impact on the power curve. It would be too difficult for us to incorporate a power curve adjustment based on the air density that you enter. So that's the first proposed feature. The second one has also come up a number of times, and this has to do with modeling turbines with different power curves and or different hub heights. At the moment, you can only model a single power curve type, so just a wind farm with one type of turbine model, and you can only model one hub height. Of course, as we see in repowering projects, in neighboring projects, you could have a mix of models. So this has been something that has come up before. The next one is to have a built-in power curve library, and I think this would be very cool. So right now you have to import a CSV with your power curve information every time you build a model. But we're thinking it would be nice if there was a library that you could access that has power curves and thrust curves built in that you could add to your collection over time, just to make it easier to access those power curves. And then the last one, so I guess just 4 new features, I miscounted. The last one is updating the software so that it can read in not only the metadata formatted specifically for Continuum, but adding in the metadata format that the folks at the IEA Task 43 have come up with. So they're trying to standardize how metadata is formatted. And we thought it would be helpful if we incorporated that metadata format into Continuum just to make it easier to ingest the data. Okay, so that is it for the proposed new features. So if everyone could give a thumbs up to 2 of those 4, that would be really helpful. And then we will get into the proposed updates to the framework, which isn't really about the features of the software. It's more about the programming language that we use and the framework that we build the software. Okay, great. Really appreciate all of the input.
Alice, I think there's one more actually.
Oh, time series losses. How could I forget about time series losses? This is a great one. So we have a time series model or a time series module in the software, but at the moment, the losses apply just uniformly to all hours of the year. But when you think about it, icing, extreme temperature, that doesn't make sense for icing losses to happen in the summer. It doesn't make sense for extreme low temperatures or high temperatures to happen in the winter. So we want to incorporate time series losses that are time-based and are not just that simplified overall loss. Sorry about that. I forgot about time series losses. It's one of my favorites, so don't know how that happened. All right, awesome. Thank you so much for all of the votes. Very, very helpful. Now getting to updates to the framework. So there are a few, I'll just print them all out so we can just see them all. Oh, back, there we go. All right, so 3 things. These have all come up from conversations with various users. The first one is having the ability to use Continuum on your own in a scripting fashion. So be able to write your own scripts, and allow you to automate your processes using Continuum. This wouldn't be too difficult. We actually kind of already do this. We just don't have a published version for you folks to use. So that's the first idea. The second one is, as you may have noticed, the software is only available on the Windows operating system. And there are other frameworks that allow us to build a .NET software for both the Mac OS as well as Linux and Windows. I'm excited about this, especially with all of the improvements in AI that we've been seeing over the last few months. We think that we can make this happen relatively quickly, leveraging AI to basically take Continuum in its current form and just translate it to this other framework and then have a version that would be usable on all operating systems, not just Windows. And then the last one is to, again, leverage AI and take all of our C# libraries, all of our C# classes, and convert that into Python. That has come up with a few users saying that they are more comfortable in Python, they're more familiar with that type of programming language. And again, AI has been just, the advances in the last few months have just been incredible. And so we're thinking that this could be something that we could do relatively easily as well. All right, so go ahead and vote on those 3. And as you are, I'm just going to look at, so yeah, it looks like time series losses has the most votes, and I wholeheartedly agree. Not much interest in the Power Curve library. That's interesting. Okay, that is really helpful feedback. So thank you to everyone who voted. Okay, people are interested in scripting. Okay. Well, while you all are still thinking and maybe voting on that, we'll just head to the final slide as we have 5 minutes left in today's hour. On behalf of myself and Erin, thank you everyone so much for attending today's session. We're excited that we're halfway through the WinFlow model explained part of the lecture series. It's going to be exciting in the next 3 as we really tie things together, and it all should come together hopefully for you all, and should have a much better understanding how the Continuum model works. Okay, Erin, any closing thoughts?
No, thank you all for joining us. Hopefully you guys are able to, yes, like Liz was saying, understand kind of the inner workings of what's going on as you're using the Continuum model, and start to think about things a little bit differently and know, okay, if I tweak this, maybe things will look a little bit how I would expect them, and how to kind of utilize the model more to your benefit.
I concur. All right, we'll stick around here for another few minutes. If anyone wants to, stick around and chat, if you have any questions, we're happy to answer them. And if not, we'll make sure to keep you posted on the next town hall. Make sure to follow us on LinkedIn as well as our YouTube to stay up to date on YouTube videos and tutorials and other updates that we'll announce. All right, thank you so much, everyone, and enjoy the rest of your day.